Hi all, this is Mr. Yeager for chemistry, and this is our last section looking at percent yield. Last section is stoichiometry, doing percent yield. So this usually involves doing mass-to-mass stoichiometry. I know I said that in my last video, but we did have to use it all the time. This one really should use mass-to-mass stoichiometry. And this one's interesting because, again, when we do mass-to-mass stoichiometry, and I guess we'll get to the definitions right away, okay? What we have happen is, I'm going with the second one, when you do the stoichiometry, you are finding what you believe you should produce, which we call the theoretical yield, okay? So that is, that we do the math in theory. If everything goes perfectly, this is how much you should produce during the chemical reaction. The thing is, and the annoying thing is, when you actually do the chemical reaction, you get what's called the actual yield out. That's what you actually make. And unfortunately, this often comes out less. And I mean, if it comes out more, it's probably because there's a lot of other stuff in it that we don't want, and we haven't eliminated that stuff yet. There might still be the excess reactant and everything. So that's stuff we do think about in the experiment. But if we do even eliminate all that stuff, we never come out to 100%. We don't get the actual amount that we think we should get from the theoretical calculations of it. And many times, we're pretty low. I mean, a lot of percent yields are like in the 30% and stuff like that. That's why things are expensive, et cetera, et cetera. I can go off on a tangent on this. All right? But the theoretical yield, big thing, is what's from the stoichiometry. The actual yield pretty much is going to be given to you in the problem, in the context of the problem. So you just have to read that, or we're going to calculate it out if you're given the percent yield. Okay? So that's what percent, and then when we get to that, the percent yield, yes, it tells you how efficient the reaction is. Be careful. Again, when we do a lot of labs, especially classroom labs, we do get percent yields of over 100%. That means that doesn't mean you have created anything. It means you haven't gotten rid of some of the impurities or the excess reactant, like I said, or other stuff like that. Okay, so it's tough, especially in a high school classroom, to get this well, where you actually usually go over versus under. But you know, it is what it is. This is your formula. Percent yield is actual over theoretical. The way I sometimes tell people to remember that is A is before T in the alphabet. So A is on top, T is on the bottom. Again, actual is what is created in the lab. Theoretical is how much you think, theoretical, think should you get. Okay? All right, so here we go. So as always, balance the equation first. I get Zn, 1Zn, 1S, 1S. I got two O's, but I got 3 O's on that side. That's going to be annoying. Put a 2 right there. I put a 2 right here, but then that puts a 2 over there, and watch what's going to happen here. So, so that puts, yeah, that gives us a lot more oxygen. So I have 2 here, I have 4 there, so a total of 6, so that's 3. I think that's right. 2Zn, 2Zn, 2S, 2S, 6, and 6. Very good. All right, so our question is, how much sulfur dioxide should be expected if 4,897 grams of ZNS are used and you're getting an 86.78% yield? First things first is we need to do mass-to-mass stoichiometry from ZNS to sulfur dioxide. So we're going to start with 4,897 grams of ZNS. I'm going from grams to moles of ZNS. I do need to get the molar mass of that. I know it's going to be 1 mole. ZNS, 9 times, not times, just plus, 32.07. I get 97.46 grams per mole for ZNS. I'm going to go from moles of ZNS to moles, what do I want? Sulfur dioxide, SO2. This looks like 2 to 2. And then 1 mole of SO2 produces 60, I'm going to calculate 32.07 plus 32, yep. 64.07 grams of SO2. So I get 4,897 times 2 times 64.07 divided by 2 divided by 97.46. That's a lot. Well, I guess we put a lot in. We believe we should get 3,219 grams if we did this perfectly. This is our theoretical yield, which I'll call TY. All right, but how much is actually produced? Well, my formula is percent yield equals actual over theoretical times 100. All right, so I'm going to basically change the percentage to a decimal immediately, and that takes care of the 100 part. So 0.8678. I mean, if you don't know what I'm doing, if I plug in 86.78, I'm going to divide by 100 at the beginning. So I'm moving the decimal point over. Equals A over 3,219. I'm going to multiply by 3,219. And my actual yield is 2,793 grams is what I actually get. All right, so mass to mass, plug it into the percent yield equation, change that percentage to a decimal, A over T, solve. All right, so here we go. Balance the chemical equation first. Mg 1, 2, 2, 2, 2, good, good, good. Okay, hopefully we're getting the idea with the balancing. If you need to take a moment, pause it and take a look at it of how I got that. All right, so 10 grams of magnesium reacts with excess HCl. So I'm starting with 10 grams of magnesium. Okay. At the completion of the reaction, 29.5 grams of MgCl2 was produced. Calculate the theoretical yield and the percent yield. All right, so first off, why am I using 10 grams and not 29.5? It's because I have to start with a reactant. I have to start with a reactant to get the theoretical yield. So Mg is a reactant, MgCl2 is a product. This right here, this number being given to you, is the actual yield. So that's how that's going to be coming out in the problem. You got to read it, and for context, we're saying when we finish the reaction, I have 29.5 grams of MgCl2 in front of me. So that's what's actually there, okay? So that number is not going to be used until the end. I need to change Mg, though, into MgCl2 to figure out the theoretical yield. So grams of Mg, moles of Mg, 1 mole, 24.31 grams is what molar mass of Mg is. I go from moles of Mg to moles of MgCl2. This is nice. It's only going to be 1 to 1. And then I go from moles of MgCl2 to grams of MgCl2. And 24.31 plus 70.9. That's 95.21 grams. So how much do we think we should have produced? 10 times 9. We think, or we say, based on our calculations, we should have produced 39.2 grams. So this is our theoretical yield. So then I do percent yield equals actual 29.5 over 39.2 times 100. And we write it out as a percentage at the end. 29.5 divided by 39.2. We will keep sig figs during this, so we do only do 3, so 75.3% is the percent yield. All right, one more. We have 0.5 grams of silver nitrate. It reacts. We want to find the theoretical yield of silver chromate. So this one's being really clear. Just find silver chromate. Calculate the percent yield if the reaction produces 0.455 grams of silver chromate. What is the 0.455 grams? That is my actual yield. Again, if you want to try it on your own real fast and then like to see my work after, make sure to pause it. If not, here we go. We got to balance it. 2 Ks, 1 K, I'll put 2 there. CrO4, again, I balanced the whole polyatomic together. I have 1 and I have 1, so I'm good there. I have 1 Ag, I have 2, I got 2, and 2 NO3s, 2 NO3s. All right, so here we go. 0.500 grams of silver nitrate. I'm going to go from grams of silver nitrate to moles of silver nitrate. 1 mole over 107.87 plus 14.01 plus 3 times 16, 169.88 grams. I will then go from moles of AgNO3 to moles of, what am I looking for? Silver chromate, sorry. Ag2CrO4, though that's going to be a big molar mass. We'll get to that in a second. AgNO3 is 2, silver chromate is 1, and then 1 mole of silver chromate to grams. Chromium 52 plus 4 times 16. That is 331.74 grams. Let's see how much we should produce. We should produce 0.488 grams. That is my theoretical yield. So my percent yield is my actual 0.455. I'll tell you, usually when we give you problems, the actual yield will not be greater than the theoretical yield. I mean, I say that, it's possible it could, but I bet you most problems we give you, it'll be less, so that you have an actual percentage that's less than 100%. When you're in the lab, be prepared that you might get over 100%. 0.488 times 100, 0.455 divided by 0.488 times 100. This is a great percent yield, 93.2%. And that's it. That's what we got for all of this stoichiometry unit. Okay, obviously there's plenty more problems to practice. You can definitely do that, and I would suggest it, and we'll go from there. All right. Thank you very much.